statics questions are, but from the onset, if you go to college for engineering, civil engineers and mechanicals all have to take a couple courses in statics. And statics, quite simply, is what it says. Things that don't move. They are in static equilibrium. So we've done statics questions before where the net force equals zero. Not a particularly complicated thing. So let me show you an example of what that might look like. Imagine I have a bridge that is a supported bridge where it has two supports, one on either end, and then the bridge itself has its own weight. If we are careful and place this in a manner that is symmetrical, this problem is pretty straightforward. Let me show you an example. Suspended by two strings, and I'm going to label those as tensions. So this is going to be tension at 80 centimeters, and this is tension at 20 centimeters, and this is the weight of the meter stick. All good? All right. In these problems, net force and net torque both equal 0. Now, this problem, though, if I wanted to figure out, say, what the weight of the meter stick was, well, I could do so probably just by using net force. In this case, because I have the tensions and I have live measurements on the tension, I think you guys can agree that one of the tensions is 0.35, and one of the tensions is 0.33, maybe 3.2. Hard to know, it keeps changing. I think I'll go 3.2. Find the weight of the meter stick, pretty straightforward here. With net force equals 0, I'll get 0.35 plus 0.32 minus weight of meter stick equals 0. We've done net force problems before. Aww. Why 4? I know why. There we go. All right, so this gives us weight of the meter stick. I'm saying 0.67 newtons. All good? All right. Now, here's what I really want to talk to you about. I have a 500 gram mass here. Now, if I place it at the center, I think you guys would all agree it's probably going to affect the two supports equally. So if I place it right there, not perfectly equal, but I think we can agree that they're pretty close. Wouldn't you? The issue comes down to what happens if I move it to one side versus the other? How would I predict what the tensions would be? And I think you obviously would know that if I get this over to one side, I'm going to have more tension over here than I am over here, right? As the weight gets closer to that support, this support's going to hold more of the weight of the system than this support. Does that make sense? How can we predict how much? If we didn't know what the tensions were going to be, like if I didn't have this live readout, and I wanted to predict what the tensions were, if I take my, I need this, I'll save that. If I take that weight and say place it over here, say at the 75 centimeter mark, and that's where I'm placing my 5 newtons. I know the weight of the meter stick is 0.67 newtons because we measured that already. If I wanted to know what the two tensions are, I think I'm going to have trouble if I just use net force. My net force equation is going to have T20 plus T80 upwards minus 0.67 minus 5 downwards. And that has to sum to be equal to 0 because it's clear to me that the meter stick isn't accelerating, so this is a first law problem. But that alone isn't enough to distinguish one tension from the other. I just know that the two tensions have to both apply an upward force equivalent to the total weight of the bridge and the load. This is where torque comes in. This problem requires that we use both force and torque to determine the size of the tension. So we'll take this, place it over here for a minute, as we talk about what it will take to use torque to figure out our problem. This is a net torque problem, and it's one where we can use net torque to solve it. So I'm going to start by placing some extra information on the problem that was not there before. I'm placing indicators of where each of these forces are applied. You'll notice I didn't draw a free body diagram in a traditional sense because we're talking about torque and force at the same time. And although forces don't care where they're applied, torques do. So where you apply a torque makes a difference. So for these questions, we'll need something that can tell us where the force is applied, because that's how torque works. Now what we're going to do here is consider that the net force is equal to 0, and we already generated a relationship there, but now we're going to do one for net torque. So the first thing we do is identify the torques acting in our system. To do so, though, requires a step here, and this step's going to be not hard, but one of those ones that you guys tend to forget. So although step 1 is to identify that net torque equals 0, step 2 requires that we identify a pivot point. But our system isn't rotating. There is no axis of rotation for this problem, neither obvious or implied. In a statics question, regardless of the actual pivot point, you can choose where to place your fulcrum. I'm going to say that again because there are cases where you might be given a pivot point, but you don't have to use it. In a statics problem where the system isn't rotating, you can choose any place to be your fulcrum. Because your system's in balance, it doesn't matter where you place the fulcrum, because the system's in balance. It is not rotating. So when I look at the fulcrum, it doesn't matter where I place it. I can place it at the end of the meter stick if I want. I can place it in the middle of the meter stick if I want. But I'm going to give you a hint. Remember, where you place the fulcrum determines where the pivot point is. The torque arm length is the distance from the fulcrum to the pivot point. So if you place the pivot point at the location of a force, you eliminate it as a torque in your problem, because the torque arm length will be 0. So one thing I would do if I were you is when placing your pivot point, I would place it at a force that you don't know. That eliminates an unknown from your equation. It doesn't make the problem much easier, but it means that you'll have one less unknown to deal with. In some of these problems, you may have more unknowns than you're aware of. So sometimes eliminating an unknown can make a massive difference. So I'm going to eliminate one of the unknowns. I'm going to place the pivot point at the location of the T20 torque. Again, step 2, place your pivot point, understanding that you can place it at the location of a force and eliminate it as one of your torques. This means I have 3 torques, though, right? Only 3 that I have to sum because I've eliminated one of them. So I will have the torque from the meter stick itself. I'm going to have a torque from the 5 Newton mass, and I'm going to have a torque from the T80 tension. These are the 3 torques acting my system. They have to sum to be equal to 0. So I'm going to set up my torque relationships. Just a reminder, torque is torque arm length times force times the sine of the angle. So for each one of these torques, I have to consider those things. So I'll set up the first one, and then you guys have to set up the others. So I know where my pivot point is. So to establish my first torque, my torque arm length is a vector that points from the pivot point to the point of application of the force. That's my torque arm length. For my first torque, the meter stick, that's going from the 20 centimeter mark to the 50 centimeter mark. That's a torque arm of 0.3. Next, I have my force that's acting there. That's the weight of the meter stick, which we already measured to be 0.67. And then we have the angle. And I think the angle is pretty obvious here, but in case it's not, this is the angle between the torque arm and the application of the force, which is 90 degrees. So I'm going to put sine of 90. Almost done, but I'll remind you that torque has direction. So for us, we could use the 3-finger rule to come up with the direction, but we'll have to choose whether into the board is positive or out of the board is positive. Makes no difference to me. So what do you guys want? Into the board positive or out of the board positive? Into the board? All right, so that means any torque that is into the board is going to be considered positive. Okay so far? So is the torque from the meter stick's weight a positive or negative torque? I mean, just looking at it, we can probably agree that it's going to make the whole thing curve this way. Don't you see that? About that pivot point? I mean, that's clockwise, but that's also using the curl rule. That would be into the board. So this must be our positive torque. So I will list it as so. Positive torque. All right, you guys do the other two. Had a few folks having some difficulty with where I was coming up with things like 0.3 and stuff like that. Let's move on to this one, and I'll walk through it again. All right, this is the torque that comes from the hanging weight. So this is the 5 Newton weight, the 500 gram mass. So the torque arm for that is an arrow that's drawn from the pivot point. All torque arms are from the pivot point to where the 5 Newton weight is acting on the system. So that's my new torque arm, and that goes from 20 centimeters to 75 centimeters. So that's a distance of 55 centimeters. So my torque arm is going to be 0.55, because I have to put it in meters. The weight I put here is 5 newtons. I'm hanging 500 grams, that's 5 newtons. And again, the angle is still going to be 90 degrees because we're just dealing with a horizontal meter stick and a downward force. This one is in the same direction as the weight from the meter stick, so I'm going to make it positive as well. Which leaves just one more. And for this last one, again, I'm still starting at where the pivot point was. But now I'm going to go all the way to the 80 centimeter mark. 80 to 20 is 0.6. I don't know the size of this force. That's the whole point. We're trying to predict the size of this force. But I do know that it's acting upwards, so that's going to be an angle of 90 degrees again. However, this one is trying to make the system go counterclockwise, so I have to make this torque negative. Now, these have to add up to be equal to 0. So 0.3 times 0.67 gives me 0.201. And then my 0.55 times 5 is plus 2.75 minus 0.6t equals 0. Just added them all up. Now, because we eliminated one of the unknowns, this generates a relationship that has only one unknown in it, making this pretty easy to do. So all I have to do now is solve for my unknown. So I'll have 0.6t equals 2.951. Just added those two things together. Now I divide by 0.6, and I'll get that tension on the 80 centimeter side is equal to 4.9 newtons. Not quite done. because I need the tension on the 20 side as well. But I already have something for that right here. So T20 plus 4.9 has to equal 5.67. So T20 looks like I get 0.75 newtons. So not particularly tough. This one's kind of a slow pitch. Let's check it out. I'll set this up as a question. I have still a support here. I have a support here. I have the weight here. But now I'm taking and I'm putting my weight on this side. And the question I'm asking is, where can I place this weight without the system becoming unstable? What's the furthest distance to the side that I can place it before the system becomes unstable? Instability occurs at the threshold where this drops to 0. Now there's probably a better pivot point to use this time than before, because if we put the pivot point where we had it, this tension's going to 0 already. That's going to make this torque go to 0. So I think there's probably a better place to put the pivot point. And if you don't know where that is, I'll help you out. Put the pivot point here. You'll be happiest. Now again, I don't want to work this problem out. I'd like you to work this problem out. So if you're shrewd, you'll understand that you're only having to deal with 2 torques. And by the way, you did this problem on Friday if you were here. This is what you did to find the mass of the meter stick. This is exactly what you did to find the mass of the meter stick. So one of the tensions is pretty well known. One of the torques is pretty well known. It's the meter stick. The other torque has an unknown in it, because we don't know what the torque arm distance is going to be. And if you haven't figured it out yet, the torque from the 20 is 0, because the tension is going to be 0. Still got to add them up and set it equal to 0, because we don't want the system to rotate. We want the net torque to be 0. So I have 0.201 minus 5R equals 0. So you guys are getting? Go ahead.
Why did you make 5R negative?
I had more space in front of the R than I had in front of the other one. And choosing positive or negative is arbitrary, so I just chose to make that one the negative one. Is it clear to you that those 2 torques act in opposite directions?
Oh, okay.
But I mean, does that part make sense to you?
Yeah, that makes sense.
Yeah. And if for those of you who are not part of this conversation but would like to be, this force is causing our system to pivot this way about that point, and this force is causing our system to pivot this direction. So these 2 torques are in opposite directions. One causing a pivot into the board or clockwise, and one causing a pivot out of the board counterclockwise. You have to make one positive and one negative. So I just happened to make the one that had more space in front of the number to be negative. Either way, this just becomes, let's see, 0.201 divided by 5. So it looks to me like I can place it at 4 meters away. I'm sorry, 0.04 meters away. Let's see. Boom arm question, generally there's 2 or 3 forces. There's going to be the obvious weight of the boom arm itself. There's going to be a tension in the cable that is holding that weight, obviously at some angle. And then often there is a load placed on the system, and the load is usually placed somewhere to maximize the problem. But it's not uncommon for that to be, towards the end or something like that. This, of course, is causing a force downwards here. There's a force this way, and there's a force this way. These are not the only forces acting in the system, though. If you're trying to understand this kind of question, there is a natural pivot point for a boom arm already, and that pivot point is here. That would be the natural pivot. You don't have to use it. The system's supposed to be at rest. You can place your pivot point anywhere you'd like, but this natural pivot might come in handy because of the other forces acting on the system that you may not be thinking about. This point is attached to your structure, so your structure is got to be pushing this way on it. For the net force to be 0, the fact that the tension in the cable is pulling to the right, the building has to push to the left to make sure that the boom arm doesn't just go through our support structure. So there is a normal force from the wall. Now this force can't apply a torque because of the direction of that force. The angle would be 0 degrees, and therefore the torque would be 0. But there's also an up or a down force from the wall. And you don't necessarily know which one it is. It will depend on how the system is arranged. This force is unknown. So when you consider the forces acting in your system, there is an unknown force that acts up or down, and you don't know which direction. Because of that, if you're asked to solve for the force from the wall, you should be aware that if you pick upwards as your direction of this force and you work it out and it becomes negative, you just know you picked the wrong direction. It's not a problem if you pick the wrong direction if you understand what you get as a result. But this is a fairly straightforward question. I mean, the only thing that gets added is an angle here. However, be aware that they will often not provide you with the angle, but they will provide you with information where you can find out the angle. Like they'll say it's mounted some distance above the boom arm, and they'll tell you where it's mounted here, so you might have to do a little trig to figure out the angle. It's not a big deal, but just be aware that that's not uncommon. But also remember, when it comes to the definition of torque, when you're trying to calculate the magnitude, the angle is the angle between the torque arm and the direction of the force. So a couple of these are 90, but obviously one of them isn't. Question that you should be able to do, and this one can be harder. Anybody ever used a ladder before? Because the ladder question is also a statics question. It's a standard force and torque question. These are a little tougher. In fact, if you're drawing this out, what you should consider doing right now is, let's assume that a person is going to stand on the ladder somewhere. So assume they're somewhere on the ladder. What forces are acting on your ladder? Maybe draw a couple of arrows in your diagram, because you might miss one or two if you're not thinking about it thoroughly. So did we get the weight of the ladder? Obviously. The weight of the person or the load? Pretty obvious too. Now let's get to the ones that might be less obvious. Did you get the normal force from the ground? Good. How about the normal force from the wall? Did you get friction from the ground? Without friction, it slides. Did you get friction from the wall? Now, traditionally in this class, for appropriate level of difficulty, we tend to say that the wall is frictionless. That does make the problem easier. Go ahead. Probably. Good pickup. And the friction from the wall does help you keep your ladder in place. Friction from the ground, though, and the wall are both static friction, so you don't necessarily know how much friction you have to work with. That's important for questions like, what's the maximum or minimum angle you can place the ladder with respect to the wall without it sliding out from underneath you? That would be a pretty complicated question, but not an unusual one. So keep in mind with these problems, they can get complex. We're going to stay with pretty much middle of the road questions, and that's what your homework's going to be like. But this question is among them. One of the things to think about is that it's often easier to take this problem and then draw the ladder differently. Part of the reason, because these two forces aren't the same. And so recognizing which forces are which and how they're acting can be really helpful. So just taking the ladder and turning it might help you figure out how to lay out your forces. All right.